I'm Randolph West. This is the first time I'm presenting this session, so I don't know what the timing is going to be like, which is going to be awesome. I hope you're looking forward to that. I have two moderators. I've got John, who's going to be doing the Q&A moderation in Zoom, and I've got Bob, who's doing it in the Slack channel. So if you do have questions, they're going to try and handle the questions, but if they don't know how to answer them, they're going to funnel them through to me. And please ask questions, because this is going to be binary. Binary is a lot of fun, so let's jump into it. I'm going to do the About Me slide, which is going to be very, very brief. I am a nerd. That is a picture of me when I was being a nerd quite a while ago, but still relevant. If you have any feedback, please fill in the form on the website link, and you will also have a QR code at the end of this session. So let's get into the basics of binary. A CPU is a hot mess of on-off switches. That's ones and zeros or bits. When we talk about bits, we're talking about ones and zeros in a CPU, memory, or on the storage. There are 8 bits in a byte, but only by convention. Some folks in the old days wanted to make bytes a little bit wider, but we settled on 8, and that seems to have been the general consensus. When we copy data from storage into memory and then from memory into CPU, it's copied as it is. In other words, however it's laid out on disk is how it's laid out in memory. It's how it's laid out in the CPU registers. And the reason for that is because it's binary all the time. The CPU doesn't actually know or care about the difference between data and commands. It's just the way it's laid out on disk depends on where it gets put into the CPU registers. It's all binary. So if you don't know how to read or understand binary, you're going to be pretty much stuck when dealing with troubleshooting computers, and in my case, disaster recovery, specifically data recovery. That's one of the reasons why I got into this particular niche or interest of mine, the special interest of how to read binary off a storage subsystem because of disaster recovery. Now, as I said, binary is difficult for humans to read and write, or it's unwieldy. So we have conventions. So normally the number of 170 in decimal, we understand what that number means, less than 200. We can write it down in 3 digits. That's represented as 10, 10, 10, 10 in binary. Fortunately, there's a convention that we use called hexadecimal, which reduces the number of characters that we need to write binary. But I don't want you to think that on disk it's stored as hex. It's always ones and zeros every time. So this convention of using hexadecimal is a convenience for us to write binary more easily, but it is not stored on disk as hex. It's always ones and zeros. But, how many folks had eggs for breakfast? The reason I ask this question is because we have a concept which comes from Gulliver's Travels, I Wish I Was Kidding, by an author called Jonathan Swift. I still wish I was kidding, from the 1700s. And we get some of our computer terminology from this book. Big endian versus little endian, because in the book, some folks cracked the eggs on the top of the egg, so the little end, and some folks turned their eggs over and cracked them open on the bottom end, or the big end. I'm not kidding. This is legit. You can go and look it up. Big endian versus little endian relates to how people cracked their eggs open in a book written 300 years ago. Not kidding. So little endian might be a little bit of a foreign concept for you to understand now, because why? Who thought of that? There was a lot of weed and other stuff in the 60s. That's all I'm going to say about that. That said, Intel and AMD use, in their x86 and x64 architecture, they use little endian. In other words, everything that is on disk is flipped around, because everything in memory is flipped around, because that's what they did in the 70s with the CPU design of the Intel x86. So everything you see in memory is flipped. It's byte reversed or byte flipped, byte swapped. That's what little endian means. It means that the higher order bits, the most important bits, are at the end of the value instead of at the beginning. That's all it means, but we've got these words coming from books that are 300 years old. Now, ARM, which is what Apple has now moved to with their desktop and laptop machines, but also their phones have always had ARM CPUs, can do little endian and big endian, but Windows chooses with their ARM compatible processors to use Little Endian because it's just more convenience. We're bad at naming things. There's no question about that. And this is just one of those things that we have to deal with. So let's explain Little Endian for the 21st century. And this is the reference to my entrance music that Anthony was referring to previously. Missy Elliott, who happens to be one of the most gifted and talented performers of our time, I think summarizes Little Endian the most effective way. Is it worth it? Let me work it. I put my thing down, flip it, and reverse it. I put my thing down, flip it, and reverse it. Little Endian. Thank you, Missy Elliott. If there are any questions, please go ahead. You can interrupt me, John. Otherwise, I will just continue with the next section. All good?
No question yet.
So you also, okay, cool. It also helps to know two's complement. I did study computer science. Well, study is a word. I did attend computer science classes at school. And one of the things that I had completely forgotten about in that class was two's complement, which is a very easy, I'll rephrase that. It's a very useful technique for storing negative values without storing the sign, the positive or the negative sign, because using an entire byte or 8 bits to store the sign for a numeric value is a waste of space, especially in the 60s and 70s when CPUs were much smaller, memory was much more expensive, and storage was ridiculous. Two's complement subtracts the absolute value from the maximum possible value to get the negative value. What does that mean? Well, if you have a 4-byte or 32-bit number, a regular integer, and you have the value of -2 of that data type, the absolute value of that is 2. So it takes the value of 2 and subtracts it from the maximum value of 2 to the power of 32. And then you are left with a result, which is in hex. Remember, hex isn't actually binary. It's just a convenient way to write it. FFFFFFE, because the maximum value, because it's 4 bytes wide, is FFFFFFF. Because if it goes one higher, then it overloads. But 2 to the 32 minus 1 is the maximum value, but 2 to the 32 is the maximum value theoretically. So 2's complement might be offset by 1 when you do your own calculation because of that. So just keep that in mind. The maximum value that you can store on disk is lots of F's, but the actual maximum value is that plus 1. So now that I've confused you with 2's complement, and that's why I think I blocked it at computer science at school, so you can blame me. Once you understand 2's complement and binary, we're good to go. Oh, and Little Endian. So when you're looking at SQL Server data types and you want to know what the data type looks like on disk, you might be tempted to use cast as var binary. And in fact, the reason I got stuck into this series of blog posts that I wrote about this is because somebody asked a very good question, which I'll give you more details about later, about why on disk, a DATETIME2 column was 8 bytes wide, but when they cast it to a var binary, it was 9 bytes wide. And I have a very good explanation for that, which we'll get into, but this is why you don't want to use var binary as a stand-in for how things look on disk. It doesn't always produce the same output. And that's because when you convert them into var binary, you need to encode metadata as well, because there's no system tables to describe what that data type is. It has to be encoded in the value itself. So in this particular case, DATETIME2 had to have the precision encoded at the end of the value. So that's why var binary, or at the beginning, that's why var binary versus what's actually stored on disk may not be the same thing. Also, it may not be Little Endian. And remember, everything's flipped with Little Endian. It's still useful for checking your work. For example, datetime, small datetime, and a couple of other things like ints all look the same. Strings as well, all look the same in var binary as well as on disk. But for things like DATETIME2, DATETIME2, we'll get into that. All right, let's not get distracted. So the data types we're looking at today are character strings. This is what Microsoft calls them. I just call them strings, but in the documentation, they're called character strings. So char, nchar, varchar, nvarchar, or you can call them car, ncar, varchar, nvarchar. I don't care what you call them as long as you know what I'm talking about. I just happen to pronounce them with a ch sound. Then we're going to talk about numerics. The numerics are the exact numerics, like integer, and approximate, like floating point. We're going to talk about dates and times. So we're going to talk about stuff from before 2008 and after SQL Server 2008, because SQL Server 2008 introduced date, time, and datetime too. We're going to talk about GUIDs, and I'm glad for those of you who watched Jeff's session that we're going to be touching on this, because I will explain to you why it has been a perception, especially if you use the wrong maintenance tasks, why there is a perception of random IO causing massive fragmentation. I will show you why based on how a GUID is stored on disk. And in a bonus round, if we have time, because again, I haven't done this session before, so I'm not sure how much time I'll actually have, we'll go into SQL variant and bit. I do have Azure Data Studio running in the background. I do have Docker running, so if you have any questions and then we can quickly do a demo together, I have that running in the background as well. The caveats for this session, because I could talk for 3 hours about this and never run out of content, we're only going to be looking at row store data. So I'm not going to be looking at column store. I'm not going to be looking at any collations other than Latin collation. Latin collation means basically words that are represented in ASCII text and usually English. And that's because we don't have time, not because I don't want to talk about it. I've presented on UTF-8 at SQL Bits, so it's not like I don't want to talk about this stuff. I love this stuff. We're not going to look at compressed data, so no page or row compression. Now, again, this is a lot to do with time, but also I haven't reverse engineered the compression algorithm yet. And once I get around to that, then maybe we can have some more content on my blog for that. We're not going to look at LOB, so off-row data and that kind of stuff, because we don't have time, and also because it's just boring, because it's just binary, right? We're going to look at in-row stuff. And we're not going to look at old data types like image and text, because they're obsolete. You shouldn't be using them. If you are using them, please don't. So everybody get down. This is binary. What does a data page look like? How many people, show of hands, that was a joke, I can't see anyone, recognize this image from Paul Randall's blog? Data page has 8192 bytes. The first 96 are taken up by the header. There's a slot array at the end of the page, also known as an offset. It's known as a lot of things, but the thing in yellow on that image, if you can see that, is the slot array at the end of the page, which tells SQL Server where each row begins. And all the rest is space for rows. Seems straightforward, doesn't it? So let's do a walkthrough. All right, I said I was going to crack open a hex editor for this session, and here we go. I'm just going to move the Zoom toolbar a little bit out of the way if I can. There we go. So this is a Mac that I'm using. This is an application called Hex Fiend, which is a free tool. It's made by somebody called Ridiculous Fish, and it is fabulous. This is a data page. On the left here, we started offset 0, and if we go all the way down, scroll to the end, we go down to 8192. So here is the slot array. This is an actual page taken from a database that I created a few weeks ago. And the premise of this example that I'm showing you right now is that I'm doing disaster recovery. That's the premise that we're going to go through here. I have a data page. I don't know anything about it. I know that it is orphaned from the rest of the table. So we need to go and have a look at what's in here, figure out what it is, and try and recover the data. Cool. So with that in mind, here is the page header. It's 96 bytes. Well, the only important byte for me as somebody who's looking at this data page is that it is a data page and not an index page, because I'm not looking at indexes. That is not GAM, SGAM, PFS, any of that kind of stuff. This is a data page. So the only byte I care about in this entire data page in the header is this one, the first one in the beginning here, 01. This tells me that it's a data page. I'm literally going to ignore everything else in here. It means nothing to me. But what is important is if we go back down to the slot array over here and work backwards, we've got 0, 6, because everything is little endian, remember? And this tells me, I'm going to zoom in a little here. That is number 96, right? That 60 is 96 in little endian in decimal format. In other words, the first row starts at 96. which makes sense because the page header is 96. And then the second value is 171. So at offset 171 in the page, we're going to see the second row. Nothing else here because this is obviously all empty space. And so we know that there are probably only 2 rows in here. That's pretty cool, I think. So let's go to offset number 96. Sure enough, we see something called a row header. A row header is always 4 bytes. Now, something that I noticed in Jeff's presentation, Jeff mentioned that when he did a fragmentation query against one of the system DMVs, it said that he had a row header of 7 bytes. That's because, and we'll get into it, that's because Jeff's query returned the 4 bytes here, as well as the number of columns, as well as the null bitmap. So that's 4 for the row header itself, 2 for the number of columns, and 1 for the null bitmap. And based on the kind of tables design that he had, that explains why he got 7 there. But in every single SQL Server row, we start with 4 bytes. That's it. What's important about these 4 bytes are tag A, which is the first byte here, which is actually a binary map or a bitmap. In other words, it's not the value 70 here. It's not the value 112. It is actually a bitmap made up of ones and zeros in a sequence, which means something for each position in that byte. Now, depending on what is in there, this next byte, tag B, will always be 0 or 1. It'll only be 1 if it's ghost forwarded record. Otherwise, it's usually only ever 0. So the first 2 bytes here tell me that this is a regular row and that there's some encoded information, which we'll get into in the slides. Then here is bytes 2 and 3, because we always start with 0, 0, 1, 2, 3. That's 4 bytes. Bytes 2 and 3 tell us where the null bitmap offset starts. Now, that doesn't mean that if we go to position 48, and I'm looking down here at the bottom here because I've got this cool tool that tells me what this value means, it doesn't mean that the null bitmap is at position 48. What it does tell me is that the null bitmap starts at position 48 in the row, because the null bitmap includes the column count. You don't know what your nullable columns are unless you know how many columns you're looking at. So the null bitmap itself is offset by 2 bytes from the column count, but it starts at position 48. Cool. You wanted level 500, you got it. So here's the first part. And if we count down to the offset of 48 bytes, then we get to here. And this is the column count. There are 2 bytes for the column count. So that tells me that there are 3 columns in total. No, I do not want to enable dictation, thank you. Which means because we've only got 3, which is less than 8, and I'll tell you why that's important now, the next byte after the column count is the actual null bitmap. This tells me there's only 3 columns, so I only have to look at the next byte for the null bitmap. If there were more than 8 columns, the null bitmap would be another byte wide, up to 16. 16 to 24 would be 3 bytes wide, and so on. So this null bitmap is 0, which means there are no null column data types in this table, which is cool. So we know that there's 3 columns. We know that the null bitmap is only 1 wide. So whatever comes next in also 2 bytes is the number of variable width columns. I know that there's variable width columns because the row header told me. I'll show you how that works. So we have here the null bitmap, which starts with the number of columns, the null bitmap itself, and the number of variable columns. So that means there are 2 columns before here that are fixed width. And then if we have a look here, 3D00, this is another offset to tell me where the variable column ends. So whenever you talk about how much space a variable width column takes up, we always say it takes up whatever's in the column plus 2 bytes. These are the 2 bytes we're talking about. We need to know where that column ends, because the width of a column for a even a var binary, but a varchar max or a varchar 200, and you're only using 3 bytes, it's going to be 3 bytes wide plus these 2 bytes that tell us where to stop reading that column. So this tells me that it is position 61. Now I happen to know that position 61 ends here. So this is the value of the varchar column. And then everything that's left over here, all the way to here, is 14 bytes, which is the row versioning. I know all of this because that's all encoded in 70. So let's get into it. Looking at a data page with a hex editor, which we've just started doing. Data pages are aligned on an 8192 byte boundary. If you're looking at the data page, you can see the actual rows, which I've just demonstrated to you. So how do you know if it's a data page? The page type is in the page header. Cool. This is exactly the same thing I've just shown you. There's the page header, the first 96 bytes. Yep, that's a data page. That's all I care about for now. At the end, the very bottom of that page, which I showed you, I scrolled all the way down, is the slot array. And that is, you count backwards from the end and it's all byte reversed. 60 is offset 96 for the first row and AB is offset 171 for the second row. Easy. Byte 0, the first byte of the record, is the record type, which is a reversed bit mask. Byte 1 is either 0 or 1. It's ghost forwarded record only. Then it's a 1, otherwise it's always a 0. And bytes 2 and 3, in other words, the third and fourth byte in the header, is the null bitmap offset. And then the fixed length portion of the row. Then it's the count of columns, which is where the null bitmap starts. Then it is the null bitmap itself, 1 bit per column. And whenever SQL Server stores bits on disk, it always uses a minimum of 1 byte. It'll never just store the single bit because it's just more convenient to store a single byte and just know from right to left, because it's little endian that the first bit in that byte means something. The next 2 bytes after the null bitmap are the count of the variable length columns, and then 2 bytes per variable column with the end offset. We know when we stop looking at the column, and we can subtract everything out. Finally, we'll get some variable column data, and then finally, doc1x will have 14 bytes of row version data, maybe, if that's what's in the header. So let's look at the header. The first byte, that 70 in my example, is a bit mask. And this is represented by the binary 01110000. But remember, this is bit reversed. So let's swap it. What's stored is the first row here. And what the actual value is we've swapped these around. So we've started from the right to the left. And the first 3 bits, excluding the first one, is the page type. If it's page type 0, we're all good. That's all you need to know. Then the next 3 bits represent flags, true or false values. NB is my abbreviation. That's not the actual abbreviation, but it tells me that in the 4th position here, 0, 1, 2, 3, 4, NB means that there's a null bitmap. If that value was set to 0, we wouldn't have looked for one. The same goes for number 5. If variable length columns was set to 0, I wouldn't have looked for one. If the row did not contain versioning, then there wouldn't have been that 14 byte section at the end of the row. That's how the first byte works in a row header. I think that's pretty cool. Don't know about you. If there are any questions yet, please let me know. Otherwise, I'm going to take a sip of water and look intelligently at the camera.
No questions so far. Doing great.
Fantastic. So we looked a little bit of this in the practical walkthrough. That is the row header. And this is due to the fact that the slot array at the end of the page said that 60 is the first position and AB is the second position. And that's what's demonstrated on this image here. Then if we look for the null bitmap offset, we know that the column is going to be, oh, I missed a 0 here. No, this is right. This is the null bitmap offset. So it's pointing to here, but I'm excluding the 0300 because that's the column count, and I'm just pointing directly to the null bitmap. So there's no nullable columns in here. So that's what's happening there. Then the column count is just before the null bitmap. I already showed you this. There are 3 columns in total. And then just after the null bitmap itself is the variable length column. And there's only one. So we know that everything before the null bitmap offset is the fixed width portion, and everything after here, knowing what the end offset is for each of the variable width columns, we know what the data is in there as well. And that's what I've just said there. 3D is the 61 byte offset. So if we're going to look at the fixed length portion of the row, I've stripped away the header. This is just the data from the end of the header to before the column count. So now we're going to try and guess what this data is. What is that? Well, if we know what we know about little endian, we know that that's probably an integer because it's the value of 1 stored backwards. So looks like an int identity column to me. And that's a good guess because there are 1, 2, 3, 4 bytes in here. Because remember, this is hex. So this is the representation of the data, 2 characters for every single byte in hex. So 01 byte flipped to the end would be an int. It's probably an int because it's 4 bytes wide and it's a number 1. So that's a good guess, which leaves us with the rest of it. So 3F00, 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 then a bunch of 20s. Now 20 is a blank space in ASCII. I happen to know that because I've done a bit of disaster recovery, and you've probably seen it as well when you're looking at just, well, I don't know what you'd be looking at if you knew that. Maybe you programmed in binary like I did. But what else is interesting here is that not only is there a bunch of 20s here, but there's also for every second character here is zeros or null, which means that this is 3F, 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 ASCII. Those are question marks. I happen to know that those are question marks because I've done this so many times. Somebody tried to store probably emoji. Somebody probably tried to store an emoji value in a nchar20 column and forgot to put an N in front of the quotes. That's a pretty good guess. So that looks like an nchar20 column. Somebody made a mistake while inserting the data. And so we just have 3 question marks instead of the actual data. Is that a page corruption? Probably not. That's just somebody making an error when they inserted the data. So let's look at the 3rd column, but now this is the entire row because we've got all those offsets to think about. So if we're looking at the entire row, including the row header, we can ignore most of that stuff because we've already established what that all is. And remember the tag a byte said that there was a 1 in the position for versioning. So we can assume that these last 14 bytes are the row version. So that means in the variable width column, we've got 3F, 3F, 3F. Looks like somebody stored the same value in the 2nd column, which is the nchar20, as they did in a variable width. So probably varchar, nvarchar, definitely nvarchar because of the zeros. So that's pretty cool. We've now discovered somebody made the same mistake for the same 2 columns. This is what happens when you forget that N when you're inserting something into a Unicode column that should have been Unicode and wasn't. I wonder who that was. There's a better way. We don't have to go through hexfiend and reverse engineer everything. There's a better way. We can use a hex editor. It's very useful for disaster recovery. But if you can mount the database and you can look at the database using DBCC page, well, why don't you just use DBCC page? It does all the heavy lifting for you. DBCC page is useful if you have the data file and the page IDs. You need the data file ID because you know which file to open, and the page ID will offset 8192 bytes times the page ID, and it'll go and find that 8192 byte section and then go and look at it. It'll go and look at the page header. And to look at everything, you need to output to your Management Studio or to your Azure Data Studio. You need to have traceflag 3604 enabled. And the best way to get the page ID is using DBCC ind, which stands for index. DBCC page and DBCC ind are non-documented because they may change, but it doesn't mean we can't use them. You could use systemdb database page allocations to get the page ID as well. But if you know how to use DBCC ind, just keep using that because it's a lot easier. Turn on traceflag 3604, go and get the indexes information and then get the page ID out of that. DBCC ind requires a parameter. I've put in -1 here because that means bring back all the index information. It'll bring back heap information, it'll bring back clustered indexes if there are any. It'll bring back non-clustered indexes. If you already know that there's a clustered index, you can just use a 1 here, or you can just use a non-clustered index number. In this case, because we don't know, we want a -1. And then we take whatever the output here is for the data page, and we're going to plug it into here, DBCC page with the file ID and page ID. File ID is usually 1 unless you've got a file group with multiple files. And then 3 is the detailed version of DVCC page, which provides the page header plus detailed information about each row. So you will get the binary. It'll dump out the binary for that row, and then it'll go and tell you for each column inside that row exactly how long it is, how much data it's using on disk, because if it's nchar 20, it's going to use 40 bytes because of byte pairs. And it's just a lot easier to figure out what's going on. And this is how I figured out, for the sake of this and the blog posts that preceded the session, of what these data types look like. So according to my watch, we are half an hour into this. So that means I have a lot of time. So I hope I got enough content. Let's look at character strings. Character strings are what Microsoft calls them. This is char, nchar, varchar, and nvarchar. Collations. One of my favorite things about SQL Server are collations. When you install SQL Server and you are a junior DBA, because that's the only person who ever installs SQL Server these days, because otherwise it's already installed, right? Am I right? So you say to the junior DBA, okay, here's the ISO, or in my day, here's the CD or the DVD. Go and install SQL Server. Okay, cool. Next, done. Cool. Now we've got SQL 1 Latin, 1 CP, 1 AI, C something. It's the default collation because that's the regional settings of your computer. Please, if you're going to install SQL Server, make sure that the collation is correct, because it picks up your regional settings for the user that you're installing as. I know. Collation, Unicode, UTF-8, terrifying. I'm not saying it's complicated. It is complicated, but it's terrifying. You should be very scared about collation and getting it right, because it affects everything. You don't want to end up installing SQL Server again and again and again because you got the collation wrong. Please, please, please make sure that you get your collation correct the first time or the second time. Now in DOS and then in Windows and therefore in SQL Server, there's some weird code page stuff. Code pages are what Microsoft tells the software that's using it how to represent data. So what does this binary mean? Does this binary 070 mean an integer? Does it mean a string? Does it mean half of a byte pair? What does it mean? So the code page is an operating system thing that says, this is how you present data. In the old days with ASCII, it didn't matter as much, but with Unicode, UTF-8, it matters a lot. So please make sure that you pick the right collation for your SQL Server instance. Collation doesn't only affect sort order. So if you have a collation of accent sensitivity and case sensitivity, so ASCS, you may have seen that as the abbreviation in your collation string. Accent sensitive means that if you've got a language like French, for example, where you've got an E with an accent and you've got an E without the accent, they'll be sorted differently. They won't be sorted together. If you have accent insensitivity, so AI, which is probably the default for a lot of US-based organizations, then the sort is going to be different. The data is actually going to be persisted differently on disk. And that doesn't just affect sort order, but storage as well. And then this is the thing that catches a lot of people out. It caught me out as well. It doesn't matter so much with char and nvarchar if you're not using a particular type of collation. But if you're using UTF-8, this is going to bite you. If you're converting an existing database from, let's say, nvarchar to UTF-8, which uses char, you're going to get caught out and you're going to truncate data. A column width is not measured in characters, it's measured in bytes or byte pairs. In other words, if you have a column that is 20 bytes wide or 20 byte pairs wide for a Unicode value, and then you decide to convert that into UTF-8, you have to take that into account, that the column might actually need to be wider than you think, because some of the characters will be encoded specially. And if you are encoding things like Japanese or Chinese that might have more than 2 bytes for a character, you're going to get bitten hard. If you're encoding things like emoji, for example, you have a social media system or you have any messaging system that is modern and you're encoding emoji, Some emoji takes up 6 bytes. It doesn't take up 2 or 4, it takes up 6 or 8 even, because they're now merging them together. So you have to be very careful when you decide on your collation that if you're going to use something like UTF-8, for example, the column width is measured in bytes, not characters. So please keep that in mind. There is a whole bunch of information in the link at the bottom there, and I think Pedro wrote most of that. So after all that stuff about collation, oh my goodness. Strings are stored as is on disk. If I take that string that is on the page there, strings are stored as is on disk, and I put the single quotes around it, it's going to store it as ASCII in whatever column I've got. If the column happens to be a Unicode column, it's going to put that 00 in between each byte. And if I put it in a UTF-8 column, it's going to just store it as is, magic, just as it is. There's no byte reversals. It's not going to flip the bytes, because why would it do that? It doesn't need to. Please always check your collation. And if you're going to use UTF-8 and UTF-16, so that you don't run into this problem that we found right in the beginning here of the 00 in between every single byte, always use this, the N in front of the quotes, if you're storing a UTF-16 or a UTF-8 string. That means it won't do some sort of implicit conversion and corrupt the data while it's being inserted. And that is very easy to do with things like UTF-8 and emoji. You'll notice that XML wasn't in my list right at the beginning of data types we're going to look at, because XML isn't that interesting on disk. It's an interesting data type, sure, and it has some pretty cool magic in the background about how it saves space with tags and things like that. But it's basically in varchar max. There are some optimizations, and if you want to index it, then it uses some fancy hidden tables inside the engine. But it's basically in varchar max if you're just looking at it on disk. So that's why I didn't call it out as a separate thing. If you do want to look at it separately, I have a blog post here about XML, which tells you what it looks like on disk. Yeah, it's boring. It's really boring. It's exactly what you'd expect to see. So let's talk about numbers. Yeah, we're moving on to numbers. Wait a bit, what's going on here? Tiny int, I get that. Small int, yep. Int, big int, all 4 of these have to do with ints, I get that. Money, okay, small money, sure, okay, whatever. Decimal and numeric, I get that, float and real. So with money and small money as a number, okay, let's see how that works. So integers, tiny int takes up 1 byte, small int takes up 2 bytes, int takes up 4, and big int takes up 8. The latter 3, small int, and big int, are signed integers, but a tiny int is not, because a tiny int only has 256 possible values. So it would be kind of a waste to make it a signed integer. In other words, it only stores 0 to 255, whereas the other ones have 0 as the midpoint, and you can have negative and positive values. Values are byte reversed because they're numbers, and that's how CPUs are good at numbers on Intel platform. And what? Small money and money are stored as int and big int? Really? Yes, really. Small money is a 4 byte, so it's int. Money is an 8 byte, 8 bytes, so it's a big int. If you look at them on disk, they are identical. Yes, there's something in the engine that figures out if you put a $sign or some sort of currency symbol in front of it, and it's got the default fixed 4 decimal place thing. All that kind of stuff is there in the engine. But when you look at it on disk, there is no difference between small money and int. There's no difference between money and big int. Even the max values, if you take that decimal place out, are identical. So if somebody says to you that you should use decimal or you should use money, or it doesn't matter. It really doesn't matter. The only thing that you shouldn't do, which we'll talk about next, is storing financial data as a floating point value. That's the only difference. Otherwise, money, small money, ints, decimal, it doesn't matter. Because once you multiply or divide these numbers out, then it matters. And then you've got to make sure your decimal places are correct. So small money and money are integers. Bet you didn't know that. Let's talk about fixed precision numeric / decimal. Fixed precision means you define the precision, you define the number of decimal places. So it's going to take up more space because you're being very explicit about the kind of data that you're storing here. Now I put a slash there for numeric and decimal because they're the same thing. They are analogous, they are the same thing. You can create a column A of decimal and you can create a column B of numeric, and then you can confuse yourself. You can actually refer to the second column as a decimal. It's the same thing. Standards, what are you going to do? But they're the same thing. They use precision, which is the total number of digits to store. So if you've got 4319 point whatever value that you're storing, that value that I just read out is 6 digits long and only a scale of 2 decimal points. So the scale is the number of decimal places. And it uses those two values together to persist the data to disk. And I'll show you how that works. The scale is the incrementing value. So let's say you have a scale of 4. So like the money data type, for example, has a scale of 4. It has four positions after the decimal point. That means in a decimal, when you're looking at a binary, it'll increment each value by 1 by that incremented value or that scale. So in your binary on disk, for a decimal value of 0.0000, you would suggest the zeros, and then 0.001 would be 0.001, and then 2 would be incremented by that value. So you would have to have 1,000 values in order to get up to the number of 1 in your 1.0. You'd have to have 1,000 values before if you're storing each of those increments. So the scale does affect how the data type looks on disk. You can have decimals with 19,5 and 19,4, and they will not look the same at all on disk. It doesn't use 2's complement because of convenience for programming. It's a lot easier to figure out what's going on if the first byte in this case is the sign. It's just easier. So for the case of decimal and numeric, 0,1 in the binary is used for positive values. I only mention this because in floating points, 0 is used for positive values and 1 is used for negatives. So I hope that isn't confusing. In the case of decimals, though, 1 is used for positive values. So here's a table for you to look at. As I just mentioned, the leading 0,1 is the sign. Why I'm showing you this slide is that you can have database storage using, this is the column, the second column in the table here. This is how it's stored on disk, this value here, based on the kind of precision and scale we've chosen on the left here. And if you cast it as a var binary, you'll see that it's very different. And the callout feature here is that for decimal 19,4, it says here 19 in hex, because this is the value 19, and 4 is encoded in the value. The value actually only starts here on after the 4. So 0001, 7CA, blah, 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 blah. Cool, huh? I think that's cool. So decimal 19 and 4 and 10 and 4, because they use the same scale, are actually persisted the same way on disk. This makes sense. If you're looking at it as a var binary, otherwise they're completely different because the encoded metadata is different. So this is why you shouldn't rely on var binary if you're comparing stuff on disk versus if in just a management studio window or something like that, or if you're doing data conversions. And here's a very big one for you to look at. Notice that all of these values here, regardless of their precision and scale, happen to be the same size. They're using the same amount of data on disk. Whereas in var binary, it's just going to blow this out by another byte. 1, 2, 3, 4 bytes, in fact. So this is just a demonstration of why you shouldn't use var binary when dealing with certain data types if you're trying to figure out what it's going to look like on disk. I'm going to take a sip of water. If there are any questions, let me know. Otherwise, I'm going to keep on going.
Keep on going. I think you're melting everybody's brain.
Halfway. Let's see how we do. Approximate numerics. Okay, cool. So approximate numerics work like as follows. You've got floating point and, well, float and real. They're both floating point data types. Float is just a wider thing, so it can store more precision. Now, precision is a tricky word because it's not that precise, and we'll get into why. If a person I invited to this call is actually watching right now, Jason, this is why I don't like it when you store your numeric, your money values as floating points. I'm going to show you why. Floating points use the closest approximation of the amount as a binary fraction. Hands up who's used binary fractions outside of computer science school. That's what I thought. It doesn't use 2's complement. I hinted at this previously. It uses a 0 for a positive value and a 1 for a negative value. Makes sense? Now, I joke about this, but the reason is because this is a standard that somebody else came up with and Microsoft adopted versus decimal, which Microsoft came up with. So that's why it's different, but it's good to keep in mind. It's great for exponents. It's terrible for financials. So let's get into it. How does SQL Server store a floating point value? I cannot actually keep a straight face when I'm talking about floating points because it's just so bad. 4513.19 is stored as that number. It's 8 bytes wide. Is it 8 bytes? 1, 2, 3, 4, 5, 6, 7, 8. It is 8 bytes wide. So why have I gone and highlighted some weird stuff at the end? Because once again, little endian, it's actually byte flipped. Now the first 3, it's not even the first 3 bytes. It's the first 3 characters, because remember, we're looking at the binary hex. This is where hex breaks down. We're actually looking at the first 3, or the first, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. We're looking at the first 12 bits of this value, which happens to coincide with 40B, is the exponent. This is how SQL Server stores a floating point. So we've got the exponent here. And I've separated here with a space because the 0 represents the sign. In this case, it's positive. And then the rest of this is the exponent. It's 11 bits for the exponent. That is how a floating point works. So if you know this, you know how to work it out. Let's work it out. 0 is the sign bit. The 1 blah is the exponent. But that looks a bit big if you're translating this in your head because you're magical. That looks a bit big for the value of 4,000, doesn't it? It does. The exponent is offset against a bias, which is a fixed power of 2. So there's a bias encoded in the floating point data type of 2 to the power of 1,023 for float and 2 to the power of 127 for real. Why? Because that's what it is. So let's work this out. The exponent is a power of 2. So we took that 1,000, blah, 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 to the power of 1,035, and then we subtract the bias. So we end up with 2 to the power of 12, which is 4,096. That's the number you expect to see when you're looking at a floating point. So we've already sort of messed around. Why is it? Well, this is the way it is. Why? Because, just because. Deal with it. It's a standard. So we take this number here, 1,000. I've just pointed to the screen, which of course you can see my finger doing. That number there, it's 1 to the power of 1035, and we're subtracting the bias, so we end up with 2 to the power of 12. So to get from that 4,096 to 4,513.19, we need to look at the significand or the mantissa. These are just words to me. They mean nothing. Basically, we're talking about the rest of the floating point thing. Remember, it's 8 bytes wide. We've already talking, so 8 times 8 to the power of 32, massive number, massive number. What you're left with is 52 bits, 52 bits for the mantissa, which is that, but it's not that because I've got a little note right at the bottom. You see it's 1 point blah. The blah is what's encoded in the data type. The 1 point is implied. Yeah, it's hidden, the hidden bit. We don't talk about it, but it's there. The one before the decimal point in the significand is a hidden bit and is never stored in the value. It's just implied. Because when we multiply this by the first part of the value, the exponent, we need a 1 in there to make it work. Okay, so now we're going to multiply stuff out. This is great. Notice that there's a repeating pattern. That's what this underline is. There's a repeating pattern here because when it converted it into a binary fraction, it's like dividing 1 by 3. You're going to have 1 divided by 3 equals 0.3333333 recurring. So this is going to have this part, 0, 0, 0, blah, 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 1, 1, 1, recurring. Okay, but we only had 52 bits to store this, so it stopped there. But it's recurring. So it's already lost information. It's a lossy value. Floating point has lost information here because we only have 52 bits to store this fraction in. So if we multiply this out, because we've lost information, it's never going to be the same value that we put in. By inserting a value into a floating point data type, you are going to lose a value. You're going to lose information unless it is a perfect multiple of 2 or a power of 2. So if it's not a perfect multiple or divider of the power of 2, you're going to lose information. Isn't that great? Please don't use this for financial data. Please don't use this for financial data. Even if you're storing a stock price, don't do it. Just store it as a money or a small money. It's just better that way. And yes, I'm going to get a lot of hell for suggesting money and small money. Why? It's just ints and big ints anyway. It's just numbers. Please don't do this because you will lose data. Right there, we've lost information. Oh, okay, rant over. Let's talk about my favorite thing, which is dates and times. I love dates and times. I love time zones. I love everything about the fact that the world that we live on doesn't work very well when you try and assign a calendar to it, when you try and assign time zones, when you try and assign perfection, because we've got leap seconds, we've got leap years, which are only valid every 4 years, except when it's a year divisible by 400. And then the earth wobbles a bit because the moon, I'm not kidding, this is all true. And then we've got, hey, I'm going off script now. Did you know that if you use a name time server, a time server, yes, sorry, not name time. So you want to go and get the exact time it is right now, yeah? And your server is more than 100 kilometers away from you, the time you get is going to be the time it was when you queried. But it doesn't take into account the latency of how long it takes for that value to get back to you. It doesn't take into account the amount of time it takes for the CPU to look at that value. It doesn't take into account the amount of time it takes to set your computer's clock to that value. So you're always going to be out of date. Always, 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 always. Even the most accurate timepiece on the planet, the Apple Watch, I'm not exaggerating, is wrong. They're all wrong. So when you look at fractions of a second, hold back a little if you're going to use 7 fractions. Why do you need 7 decimal places for time? You don't, probably. Yes, there's a small group of you who work for CERN, but you're not using SQL Server, guaranteed. You can't afford the licensing because you've got this massive system. So please be mindful about the data type choice you have when you're choosing a date time too. And this is why, because time is meaningless. You want to know time relative to each other, but when you start measuring stuff at that scale, it's meaningless because you're going to get noise in the system, measurement overhead, if you like, or observer overhead. So keep that in mind. So dates and times in SQL Server, cool. Do you remember DATETIME? I remember DATETIME. Jeff Moden, who just did a presentation now about GUIDs, we've had words back and forth on my blog in the comment section about why you shouldn't use DATETIME. Jeff is a proponent of DATETIME because it uses ANSI standards. Fair. You can do addition and multiplication and subtraction from DATETIMEs because they follow the standard. That is a fair comment. But if you're storing dates and times and you don't need to do that kind of stuff to it, please use the new data types. And I'll get into it about why. Date, time, DATETIME 2, these were data types that were introduced in SQL Server 2008. If you are still using DATETIME and you're not using DATETIME 2, ask yourself why, because we're talking about a product that came out 13 years ago. Then William Asaf, who is one of the co-authors of 2 books that I've written, he really loves the DATETIME offset data type, and that's why I've included it here, but I would have left it off otherwise. So this is for you, William. And if you're not watching, I'm going to come find you. And then small date time, please don't bother. Please just don't use it. We'll look at it in the demos if we have to, but please don't use small datetime. Pointless. So let's talk about datetime itself, the Sybase data type that came with SQL Server when Microsoft bought it. And we'll talk about the date portion. So datetime consists of a date and a time smooshed together. Smooshed is the technical term. A date time in total is 8 bytes wide, and it's not byte swapped. Isn't that interesting? So the first 4 bytes of a date time are the date portion, and the last 4 bytes of the value are the time. The value of 0 is 1900, 1st of January. And if you want to go to 1899, then you use 2's complement for those first 4 bytes. So if you see a value in the date time on disk and it says FF something, then it's before 1900. Cool, huh? Excuse me. And then of course, the earliest value that you can store with a date time is the 1st of January, 1753, because the Gregorian calendar changed in 1752. So instead of worrying about that, because honestly, if you're doing anything remotely related to a calendar or dates before 1753, it's probably not going to be in a SQL Server accounting system, right? Doesn't mean you can't put stuff in there, but if you're going to use values from before 1753, you need a different data type. Let's talk about the time, the second 4-byte segment in a date time value. They're rounded to 0, 3, or 7 milliseconds. Oh man, how many of you have been caught out? I've been caught out by this because we go between 0, so midnight, 0.000, and then 0.0999, and we get caught out every time because we should have put 997, because in date time data type, you have to have your milliseconds rounded down to 0, 3, or 7. Awesome, right? Well, why? Why? Jeff Moden had the answer, so did Joe Selko. But Jeff's answer on my blog, again, it's 1/300th of a second. That's why, because that's how computers worked back then. And it's 3.3 milliseconds. So 3.3 is rounded down to 3, but 6.6 is rounded up to 7. But that's why. It's that simple. I mean, people wonder why things are the way they are, but they don't have any context or history for the reason. That's a good reason for having 0.007, I think. I don't maybe like it. I have to keep in mind the 997 if I'm doing between and all that kind of stuff, or less than or greater than, but at least I now know why this is the case. And so therefore, because we are encoding stuff on that kind of boundary of 3 or 4 millisecond boundaries, the value of the 4-byte value in hex of 0002 is actually 7 milliseconds past midnight. And 3 would be 10 milliseconds. And 4 would be 13 milliseconds. And 5 would be 17 milliseconds. Cool? Cool. I think that makes sense. By the way, this is something that came from that conversation on my blog. Jeff did an article about calculating duration using datetime start and end dates in a series called SQL Spackle on SQL Server Central. That is the link to go and find it, or you can just Google it. But there's a lot of fascinating stuff you can do with datetime, with addition, subtraction, that kind of stuff, which Jeff pointed me to. So if you are going to do that kind of stuff with datetime, this is how to do it. I think that's pretty cool. I see there's a Q&A little thing on the screen. Is that a question?
Yeah, we have a question around money data types from Peter Shore.
Yes.
Yes. He understands where you are coming from. However, money is not a valid data type to the best that he knows for C# or Entity Framework. How do you balance your excellent point about storage versus the high risk of implicit conversions?
If you're going to store monetary values, use decimal 15,4, which is basically the same features that you would get out of money, but allowing you the flexibility of compatibility with existing systems, application code, that kind of stuff. So the money data type effectively gives you 15 before the decimal place and then 4 after the decimal place. So just use a decimal 15,4. That's what I would do. I hope that answers the question. Good question, though. Thank you.
Hey, Randolph,
All
it's Bob. Can I
right.
butt in with one more question here from Slack?
Yes, you may.
All right, this is from William Asaf, and he asked, question for Randolph, what is your favorite SQL Server data type and why is it DATETIME offset? And I must point out that William asked that before you put it up on the slide about him, so I think you're obligated to answer.
Which means that he's watching.
Yeah, that too.
There's a thing that we have as presenters where we say there's a good question, which means I can answer the question. Then there's a great question, which means there's a slide that answers the question. So I'm going to answer William's question with a slide that'll demonstrate why I think DATETIME offset is a pretty cool data type. It isn't my favorite, William, sorry, but I will show you why it's a pretty cool data type. Thank you for the question.
No problem.
Anything else before we move on?
Actually, one more just popped up in Slack. Theo asks, wasn't the fractional part of DATETIME, and he goes 0.5 or 0.5 equals 12 o'clock? Perhaps I'm reading it wrong, but that's how it was typed. You can always look at it later if that helps.
Do you know what? If you remind me when we get into Azure Data Studio, let's have a look at that. Let's confirm that. It's a good question. Let's confirm it with a demo.
Okay.
Cool, thank you. So let's talk about the date, the new data type that was introduced. I say new, but it was 13 years ago. Come on, folks. Let's talk about the date data type. It's 3 bytes wide. It's byte reversed. It is the number of days since the year 1, January the 1st. Now, there was no January the 1st in the year 1. And the reason it doesn't start in the year 0 is because there was no year 0 either. We went from BC to the year 1. And even BC was a misnomer because we're talking about calendars that were based on other calendars that were based on Roman stuff. And then we had the whole Gregorian thing in 1752. So if you're going to store values from before 1753, you're going to also need to store some context about those dates. Nevertheless, this value here, the date value, matches the C# data type, the .NET data type for DATETIME, which stores anything from the year 1, January the 1st, through to the year 9999. So it's going to suffer from the year 10,000 problem, but that's not our problem. None of us here has to worry about that. Max value is 12th month, 31st day. So December 31st, year 4 nines. Cool. The max value means, therefore, it can never store Fs because we'll never get there. But it does mean that if SQL Server still exists in the year 9999, then a version bump will just need to allow you access to dates later than that value because it's 3 bytes and 3 bytes is more than enough to store past that value. It just so happens that it can store up to 3 million days from year 1. That's byte reverse, by the way, because of course it is. So let's talk about time. We know that the date is 3 bytes, so the time can be anything between 3 and 5 bytes wide. Cool. Why is that? Well, I'll answer that. My dogs are currently barking, so I hope you can't hear them. All right, so let's talk about time. 3 and 5 bytes wide. You can store precision of, in other words, decimal places of your seconds from 0, which means it just records the seconds, through to 7 decimal places. And 7 decimal places means 1/100th. No, it's 1/100 nanoseconds. There's 10 million 100 nanoseconds in a second. It is a ridiculous number. Oh, there we go. Time 7 has a scale of 100 nanoseconds, which is 10 million possible values in a single second. That is such a small amount of time that it's practically meaningless. And the reason for that is because a CPU cycle is 4 nanoseconds, right? But a ping from here to downtown Calgary, which I can see from my balcony, is about 6 kilometers away. A ping is measured in milliseconds. You probably don't need to store 100 nanosecond scale. Please think about it. What I like to do is datetime 2, or time 3. So 3 decimal places, which is millisecond accuracy. And you don't have to worry about that 037 story. It's just every millisecond can be stored accurately. So that's what I use. You can use something smaller than that, but why? So datetime 2 smushes date and time together. We've spoken about the smushing, it's a technical term. This is completely byte swapped. So if you look at it on disk, you'll see the time portion backwards first, then you'll see the date portion backwards, because everything's backwards. It's Missy Elliott. It is between 6 and 8 bytes wide because you've got the 3 bytes for the date and the 3 to 5 bytes for the time. Datetime 2 is a 3 decimal places, is a drop-in replacement for datetime, and will save you 1 byte per column per row. That is cool. That is free space that you can save by converting a datetime value to datetime 2.3. And in most cases, I say most cases, it is fully compatible with datetime if you're looking at application code. If you're looking at T-SQL code that expects datetime to be in a certain format, like Jeff Moden's argument, which is expressed in the SQL Spackle series about dates and times and arithmetic, sure, that is the exception to the rule. But in most cases, datetime 2.3 is a drop-in replacement for datetime, and you'll save yourself some data, which I think is cool. I put a little star there because, you know, it depends, and we're in a 500 level session. Uncompressed row store, you'll save yourself the space. If you're using column store, you're using 8 bytes, and if you're using, and then it's compressed, and then blah. If you're using row compression and page compression, it's also compressed somehow magically, blah. So I'm only talking about uncompressed row store data here. In my experience, most people use that, so I don't think it's a big deal to say that it's a drop-in replacement. So here's a big table with a lot of things going on and stuff that's repeating and what. What I'm demonstrating here is that just like with decimal having the precision being different, means that the value will look different on disk. So datetime 2.7 all the way through down to datetime 2.0. Remember what I said before, the datetime 2.0 doesn't store any decimal point places after the seconds. So if you're looking at datetime 2 of 0, it won't store any fractions of a second. Datetime 0, so datetime 2, 0, 1, and 2 all use the same amount of storage. Check this out. That's your 6 bytes. Then if you use datetime 2, 3, 4, that uses 7 bytes. And then if you use 5, 6, and 7, it uses the full 8 bytes. In this blue section here, this blue part of the value, that is the date value. The date value is persisted, as I said before, in reverse, but this value here is the number of days since the year 1. So 737,000 days have gone by since the year 1 for this value of 2020, 22nd of April at 10 a.m. And then the time in binary, this is the bit that changes depending on the scale. So if you're looking at 7, which is 100 nanoseconds, you've got this very big number here, 363 billion. Then as soon as we start chopping the last value off or rounding it up, because that's what it does, it rounds up for each loss of information as it goes down the chain, you'll see that the value itself changes because obviously it would. It's obvious when you look at it this way, but it's not obvious when you think about it, well, datetime 2.3 versus datetime 2.4, well, maybe it just chops off the last byte. It doesn't work that way. So that's why I'm showing this to you. These numbers take up a fixed amount of bytes, as I've already mentioned, and that's why it may look a little different, but these are the encoded values for these precision, if you like. William Asaf, this is for you. Here we go again, technical term. Datetime offset also smushes the date and time together, but then it goes and puts 2 bytes on the end. But because we're doing the Missy Elliott thing of Little Indian, those 2 bytes are now at the beginning when it's persisted on disk. But in your head, think of it as being in reverse. All times are stored as UTC. So if I were to be asked why I like datetime offset, this is why I like it, because it means that every single value in that column on disk is stored as UTC. You don't have to worry about time zones because it's encoded in the value. That's what those extra 2 bytes are for. The last 2 bytes are the UTC offset in minutes. You can have a UTC value of wherever Greenwich Mean Time is, UTC 0. That's where it's counted from. And then if you go east, well, if you're looking at me, east is that way, but for me, east is that way. So if you go east, it's plus UTC. And then if you go that way on the way I'm looking at things, it's minus. So I'm currently in Calgary, which is -7 hours, but it's measured in minutes because you have places like India, which is 12.5 hours from where I am. You've even got a place on the east coast of Canada that is off by another half hour. I think that's amazing. I believe, I stand to be corrected here, but I believe there was a European country, I think it was Holland, that was 17 minutes off UTC. I may be incorrect, but I believe it was Holland and I believe it was 17 minutes. And so it's much easier, instead of trying to do hours and minutes in 30-minute segments, it's just better to encode the minutes because we're only talking about 840 minutes. And because we've got positive and negative, we use 2's complement to store that value. So that means we can store 1,680 different values for the UTC offset in minutes in that 2 bytes at the end of a date time offset. So I hope that answers that question. Yeah, I think so. I think we're good. We have, what, 5 minutes to go, right?
Yep.
We're going to go over time, so that's cool. GUIDs. Unique identifier. What is a GUID? Well, Jeff told us all about why GUIDs are not as bad as you think. GUIDs are universally unique identifiers. They are 16 bytes wide, or 128 bits. I put a little note at the bottom there that says, please do not use GUIDs as strings. Do not store a GUID as a string. Do not store a GUID as a string. You're not doing yourself any favors. Jason, I'm looking at you. I know, we'll get there, but do not store GUIDs as strings. You're wasting at least 20 bytes per column per row. And if you're storing them as nchar or nvarchar, you're wasting up to 72 bytes per GUID plus the extra 2 bytes if you're using a variable width column. Please don't store GUIDs as strings, please. They are unique with a star across multiple environments and time spans. In theory, because there's no way that we could possibly figure out if there's going to be a collision until it happens. There's just not enough computing power. 128 bits is a very big number. That's why encryption uses 256 bits, because that's an even astronomically bigger number. And encryption for a lot of internal SQL stuff also uses 128-bit encryption. So 128 bits is a very wide amount of data. There's just no way that we know for sure whether something will be colliding with another value, but in theory, GUIDs are unique. They're generated without needing a central repository. This is the main attraction. You can generate a GUID in your application and you can do a whole bunch of stuff. And then you can insert it into the database as a new record. And that will usually insert without any collisions because it's a unique value. That is its attraction. You don't have to rely on a ever-increasing monotonically increasing big int or whatever the case may be, because it's already calculated. So you don't have to have that problem with hotspot at the end and all that kind of stuff. GUIDs for development are very, very useful. For performance, well, if you're doing the regular maintenance tasks of best practice of the reorgs and all that kind of stuff that Jeff spoke about, you're going to run into trouble. You are. But if you do it the right way, then they're very, very useful. Yes, they are wide. They're double the width of a big int. But with that, you get a lot of benefits that eliminate hotspots and a decentralized generation point. So as with everything in SQL Server, it depends. Make sure that you measure the performance impact of GUIDs versus big ints or ints. Just measure it. Maybe your database is so massive that you cannot use GUIDs and you decide to use ints, and then you'll have to take that into account as well. So just please test everything. What else about GUIDs? They're designed to generate 10 million identifiers per second per system. The sort order is interesting, which is what I really wanted to show you today. There are 6 segments of a GUID that are involved, and there are 5 of them separated by hyphens because 2 of the segments are combined. So if we look at an example of a GUID here, We've got the time low, we've got the time mid, we've got the time high inversion, and that's the first 4 segments. Then we've got the clock sequence and reserve and the clock sequence low. These two values are the two that are combined. And then we've got the node. 422116. Those are the 16 bytes that we spoke about. And this is how it's stored on disk. Time low, time mid, time high, clock sequence, clock sequence. All of these are stored in reverse. Well, obviously these are only 1 byte each, so they're not technically stored in reverse because there's nothing to store because there's only 1 byte each. But all of these are byte reversed except for the node. Who wants to tell me why? Why is the node not byte reversed? Well, I'll tell you. It's the MAC address where it used to be. And that's why it's the sort order. Huh, the sort order, I hear you scream. How is that possible, Randolph? Well, it's true. Where are we at? If we have a whole bunch of GUIDs, here's a whole bunch of GUIDs, and we decide to sort them. I'm going to make this bigger, don't worry about it. It's going to sort on the node, which is the final value here. So on disk, we have, this is the sort order right here, this section in bold, which is the node. Everything else before that is not sorted. It's just this part that's sorted on disk. So that's why GUIDs have such a bad reputation when it comes to fragmentation, because they are that random that it depends on the node. And because the node is now pseudo randomized, because we're not using the MAC address anymore, the pseudo randomized value makes it even more random. So when you're storing GUIDs, keep this in mind. You do need that headroom in the top of your page. You make sure that you only fill up 80% of the page, or Jeff's recommendation, 70 to 80% of the page is filled so that you have room to grow. You need that growth so that GUIDs can be used appropriately. Do we want to do SQL variant and bit? It's up to you because we're at time.
We are at time. There are no questions other than I have a question for you.
Yes.
In the beginning, you used the hex editor to examine a row in the data page, and there were 2 rows on that data page, but you never looked at
yes, they
the
were.
second row.
Okay, so so you want to know what this value here is?
Yes.
Okay, cool. So this is 3ED826DD. Okay, well, there's 2020 here. So, okay, so let's do 3D00. So this one here, because it's basically the same value in varchar. So let's just go and drop that into Azure Data Studio and connect to my database. And oh, look at that. Coincidentally, I happen to have the very same byte stream ready and waiting for us to convert into nvarchar. Well, let's see what it actually says. Oh, look, it's the face palm emoji. Oh, isn't that cute? Well, thank you for asking that plant question. That was great.
Awesome.
Thank you. Oh, and by the way, the face plant emoji, if you put it in without the N in front, always returns 3 question marks. So that's the 3F that you saw. If you want me to get into SQL variant and bit, I will be happy to. Otherwise, I can end the session now. Let me
You
know.
can go for another 8,
10
9 minutes.
9
Yeah.
minutes.
That is more than enough time. So let's do this. SQL variant is a chimera. Chimera is a hopefully fantastical creature that doesn't exist in real life because it's made up of 3 different parts. There's a lion and a dragon, and it's scary. But SQL variant is the same thing. It tries to be all things to all people, and as a result has some limitations. You cannot please all the people all the time. That's not to say you shouldn't ever use SQL variant, because in fact, SQL Server itself contains, what's the table called? Oh yes, the configuration of SQL Server itself is stored in a table with columns that have SQL variant. So it has its uses. Don't not use it because it looks bad to you. It may have a use case for other folks. The only thing you should never do is auto shrink in the database. That's the only thing you should never do. So in SQL variant, you can store strings as ASCII or UTF-16. Notice that it doesn't say UTF-8. That is because I haven't tested it. It's not because it's not there. I don't know if it's supported. I have not tried because it depends on the collation of your database. if you try and insert a value into a SQL variant column with a explicit collation that uses supplementary characters that supports UTF-8, which was announced for SQL Server 2017. Oh, sure, maybe it'll be in there. I don't know, I haven't tested it, but I do know for sure that it stores ASCII and UTF-16. It's not fully ODBC compatible. So depending on the ODBC library that you're using, your data might not come back the way you expect. It might actually come back in binary. And that's a clue of how SQL variant stores data, because as I said before, it's all binary all the time. Each value has a prefix indicating its type. So remember when I showed you that example of the decimal value that was in var binary versus the decimal value on disk, and they were different because the var binary value had the prefix in the beginning of it. This is that, but inside the database engine. So the character prefix, so when you're storing a string, the character prefix includes the actual collation as well. Well, it has to. It has to encode it because when you, for example, create a regular table in SQL Server, you tell it, okay, this is column A. Column A is going to be decimal 19,4. Column B is going to be a varchar 20. That kind of metadata is not available when you declare something as a SQL variant. So you have to encode it in the column itself. The integer prefix, so not string, but integer, includes a version number, which has always been one since at least 2008. So my name with an N in front of it, because we're indicating that it's a Unicode value, my name is encoded as, if you were to do this in a normal binary conversion, it would be whatever's in bold here. 52 is the capital R, and we've got the 0 in between each character because it's Unicode storing an ASCII value. So capital R is 52, and then lowercase a and DOLPH is 61, 6E, 64, 6F, and so on. So here, this part in the beginning here is the prefix, E701401 blah. So E7 is system type 231. If you've ever gone and done a select from sys.types, you will get a list of values, and at 231, it'll say nvarchar. That's what that value means. So what's the rest of it? Well, I'll tell you. You can use something called SQL variant property with underscores, which is a system function which tells you all of these properties and what they mean. And it includes collation, precision, scale, and total bytes. Now you'll see here, there's a bunch of zeros in here because there's no precision and scale for a string value, but there might be if you're storing a number of some sort. So SQL variant is convenient if you need to store like a key value set and you don't know what the data type is going to be. That's cool. In fact, that's what I use SQL variant for in one of my database designs in a configuration table, oddly enough. But you can also use SQL variant for other stuff. And if you do, keep in mind that the string or the binary value is going to be much wider than you think. And let's finish with bits. As I said right in the beginning, anytime SQL Server stores a bit, it uses at least 1 byte. It doesn't ever just store the bits on their own. If there's more than 8 bits that it needs to store, then it creates another byte and starts again, and everything's stored in reverse. So when you've got a bit column, each position in the bit mask, and we looked at a bit mask right in the beginning with the row header. This is a similar concept. Each position is the true or false value. And that, folks, is that. If you need to get hold of me, email address, blog, which I looked at a couple of times. Please don't follow me on Twitter. If you're looking for SQL Server advice, that's not what I do there. My Twitter account is my personal account. At your own risk, follow me by all means, but don't expect SQL Server content. And thank you, 8KB, for accepting the session. I've had fun. I hope you have. And over to everyone else, I'm going to stop sharing.